I'm analyzing the parameters of scikit-learn's GaussianRandomProjection tool, which we use for shrinking the size of our data while trying to keep the important relationships between data points intact. We'll focus on how different settings affect the accuracy and speed of this process. This question tests your understanding of how the GaussianRandomProjection tool's settings affect its behavior. You need to determine which statements correctly describe its actions. I'll start with this statement because it's straightforward. The "eps" parameter doesn't directly set the number of final features. While a smaller "eps", meaning we want to preserve distances more accurately, will often lead to a higher number of components. It's the "n_components" parameter that actually dictates that. Think of it like this. "eps" sets a goal for accuracy, and "n_components" determines how many features we'll use to meet that goal, or as close as possible. This is true. Increasing "n_components" means we're keeping more features. This directly increases the number of calculations needed, slowing down the process, just like carrying more luggage makes traveling slower. The "random_state" parameter is super important. For reproducibility, random projection techniques use randomness, but by setting this parameter you're essentially setting the randomness seed. This guarantees that the same sequence of random numbers is generated each time your code runs with that same seed. This means that you'll get the exact same results each time, which is incredibly useful when trying to reproduce your analysis or share your work. Let's discuss "eps". A smaller "eps" value, like 0.1, means you're demanding greater accuracy in preserving the distances between your data points after the dimensionality reduction. A larger "eps", like 0.5, allows for more approximation and faster computation. These are the three key parameters in scikit-learn's GaussianRandomProjection function that I need to understand to solve this dimensionality reduction problem. "eps" controls how accurately distances between data points are preserved after the projection. A smaller "eps" means better accuracy but might need more components. "n_components" sets the number of features I want after the reduction. "random_state" is the seed for the random number generator. Setting it ensures I get the same results each time I run the code, which is super important for reproducibility. This is the core technique used here. I'm using GaussianRandomProjection to transform my data from a 1000-dimensional space down to 500 dimensions, hopefully without losing too much information about the relationships between the data points. The goal is to reduce computation time without sacrificing too much accuracy. It's like simplifying a complex picture without losing the essence of it. This is the actual multiple-choice question that tests my understanding of the GaussianRandomProjection parameters and how they influence the dimensionality reduction process and its accuracy. I need to carefully evaluate each statement based on my knowledge of these parameters. I interpret "eps" as a parameter controlling the accuracy of distance preservation in the dimensionality reduction. A smaller "eps" value, like 0.1, means I want to keep distances more precisely, which usually needs more components. Conversely, a larger "eps" like 0.5 allows for more error in distance approximation, thus potentially needing fewer components. Think of it like this. "Eps" is how much wiggle room I'm willing to allow when it comes to how close the distances between my data points stay after squeezing them into a lower dimension. This parameter sets the number of features I want after the dimensionality reduction. It directly affects computation because a higher number of components means more calculations are involved when projecting the data into the new space. It's like deciding how many ingredients to keep in a recipe. More ingredients, components, mean more complex cooking, computation. This is crucial for reproducibility. Random projections use randomness, but setting this parameter seeds the random number generator. It ensures that the same sequence of random numbers is used each time I run the code with the same seed. Thus the results of the projection will be identical. Imagine a recipe that depends on randomly adding spices. _random_state makes sure I always use the same random combination of spices. I see that EPS controls how accurately we preserve distances between data points after we shrink the dataset. A smaller EPS, like 0.1, means I'm aiming for higher accuracy. That usually requires more calculations, and thus more computing power, to achieve. A larger EPS, like 0.5, means I'm okay with sacrificing some accuracy to save time and resources. It's a trade-off between precision and efficiency. This parameter simply dictates the final number of features you want after the reduction. If I increase this number, I'll be doing more computations to project the data onto a higher dimensional space, so the process takes longer. Random projections use randomness. Think of it like shuffling a deck of cards. The results vary each time. But by setting a random_state, I'm essentially providing a seed value to control this randomness and generate repeatable results. It's like using a specific set of instructions for shuffling that always leads to the same shuffled deck. This is useful for ensuring that experiments are reproducible. Okay, let's dive into the parameters of scikit-learn's GaussianRandomProjection. I'll explain how each one affects your dimensionality reduction. It's all about balancing computational cost with the accuracy of preserving distances between your data points. Get ready. We start with a dataset that has 1,000 features. That's a lot of information. Imagine each feature as a different characteristic of your data. The goal is to reduce this massive feature number, making the problem manageable and computationally cheaper, without losing too much information. Our target is to reduce 1,000 features down to 500. Think of this as summarizing our data using the most important information and reducing noise. This is dimension reduction. The trade-off is accuracy versus efficiency. We want to achieve this reduction while maintaining important information in your data such as distances between data points. This is the core question of the quiz. We're asked to choose which statements regarding the GaussianRandomProjection parameters are true. It's a test of how well you understand what each parameter does. Let's tackle each statement one by one. Absolutely. The _n_components parameter specifies the number of features you want after the reduction. Increasing this value means you're keeping more information, which leads to more calculations and thus higher computation costs. Imagine trying to fit more information into your new compressed space. It takes more effort. Nope. The _EPS parameter actually controls the accuracy of the distance preservation, not directly the number of components generated. A smaller _EPS value aims for better accuracy, but it indirectly influences the number of components needed, because achieving higher accuracy usually demands more features to preserve distances, thus increased _n_components . Yes, the _EPS parameter determines how well the pairwise distances between data points are preserved after projection. A smaller _EPS like 0.1, is stricter and guarantees better distance preservation than a larger _EPS like 0.5. The more strict your accuracy requirement, the more computational cost it requires. Exactly. Random projections involve randomness. To ensure you get the same results each time you run the algorithm, set a _random_state . This seeds the random number generator, making it deterministic. It's like setting a starting point for the randomness. You'll always get the same, random, path from that point. I'm focusing on the parameters of scikit-learn's _GaussianRandomProjection for dimensionality reduction. These parameters control how the algorithm works and the quality of its output. We'll explore each one to understand their effects. This parameter, EPS, controls the accuracy of the distance preservation. A smaller EPS value means I want to keep the distances between data points more precise, but it might require more computation. Think of it like this. If you want a really accurate miniature version of something, you need more detail, which takes more time and effort. This parameter sets the target dimensionality. In other words, I'm deciding how many features I want after reducing the data's dimension. More components mean less reduction, but also more computation. Just like if I want a large-scale model of something, I'll use more materials and spend more time. I use this parameter to make the projection reproducible. Random projections are, well, random. Therefore, they'll create different results each time unless I use a random_state . Think of it as setting a seed for the randomness. A starting point that makes the random process predictable. This is very important for scientific experiments so that I can reproduce results. This means, we start with a dataset having 1,000 different characteristics. For each data point, think of it like describing a person with 1,000 different measurements, height, weight, shoe size, and so on. We want to reduce this number. I want to reduce the number of characteristics describing each data point from 1,000 to 500. This is like summarizing a person with only 500 key aspects. Still trying to capture the essence of the 1,000 original features. I'm using a specific tool in the scikit-learn library called GaussianRandomProjection. It helps reduce the dimensions of my data, while, hopefully, keeping the important relationships between data points intact. This refers to the accuracy parameter in the Gaussian random projection method. A smaller epsilon value like 0.1 means I'm demanding higher accuracy in preserving the distances between data points, compared to a larger value like 0.5. Increasing the target dimensionality, in underscore components, means I'm aiming for a higher dimensional representation after reduction. Naturally, this will take more computing power and time. It's like trying to write a more detailed summary. It takes more effort. The random_state acts like a seed for the random number generator, ensuring that I get the same projection every time I run my code with the same seed. It's like following a recipe exactly to get the same cake each time. This statement is false. Epsilon doesn't directly set the number of components. It affects how many components are needed to achieve a certain accuracy in preserving distances, but the actual number is controlled by the in_components parameter.